So now we will start one more very important concept of thermodynamics, that is the free energy. We have already discussed spontaneity, spontaneous process. So that was all about second law of thermodynamics. And there is a third law of thermodynamics also present, and that mainly focuses about the free energy. So today's main agenda will be to understand what is this free energy and the different aspects of the free energy. Just yeah, now free energy. This is what we have to start today. So first we will look at thermodynamic temperature with a different perspective. Because temperature to we already know. Thermodynamic temperature. So we have already seen the efficiency of a heat engine, and there was one formula. If we can relook at it, just let me show you that formula, which we discussed the previous session. This. So here we can see that the temperature is related with efficiency. And using this formula, I can have one thermodynamic definition of temperature. Like that is what we are discussing. I can say that Tc, which is the temperature of the sink, it is equal to 1 minus mu, which is the efficiency, and Th is the temperature of the source. Because in thermodynamics, we have already seen that we can convert the heat energy into the work, and how we can do that by maintaining a source and a sink, and we have to maintain the source and a sink at a constant temperature so that the flow of heat we can utilize to derive some work. And when we derive the work, there is a concept of efficiency, output upon input. So based on the efficiency and the temperature of the source, we can calculate the temperature of the sink. And this is the formula for that. Temperature of the sink, that is the temperature of the old object, 1 minus mu temperature of the source. And this we call it as the thermodynamic temperature scale. So this formula which we have written, so this is basically the thermodynamic temperature scale. Thermodynamic temperature scale. And similarly, we have one more very interesting concept, that is the Kelvin scale. That also we'll discuss. So we are discussing thermodynamics. So here we looked into the thermodynamic temperature scale, and similarly we have one more concept, that is the Kelvin scale. That is also like bit important. Let us focus on that. What it means, Kelvin scale. So the idea is that water, like the temperature of water, temperature of water at its triple point. Temperature of water at its triple point. And what is this triple point? Triple point is the point where which water exists in three states together, coexist. Like what are the three states? Solid, liquid, and gas. So temperature of water at its triple point. The temperature of water at its triple point, and it is considered to be the TH. It is considered to be the TH. That is the temperature of the hot source. And what is this temperature? Like experimentally, it is been found that this temperature is 273.16 Kelvin. And in degree Celsius, it is around 0 degree. So this is the idea. So Kelvin scale, we are very familiar with that in chemistry. In most of the numericals, you will be dealing with a temperature either in the degree Celsius or in the Kelvin. And in the Kelvin scale, the temperature of the water at its triple point, it is treated as the TH. And thermodynamic temperature scale, this formula. So this is very clear to us. Now we will be discussing free energy and spontaneity. Like spontaneity we already know. Now we will see like how free energy and spontaneity are related with each other. Free energy and the spontaneity. Free energy and the spontaneity. We have already seen one very important equation that says that entropy change, like the total entropy change, it is equal to change in entropy of the system plus change in entropy of the surround. So total entropy change is change in entropy of the system plus entropy change of the surround. Now, few points we will focus on observations. It is not always easy to know the entropy change of both the system and the surrounding. Like it is not like we have a device and we can calculate the entropy change. For that, we have to apply some certain techniques, and it is not easy to determine the change in entropy of the system and the surrounding. That is understandable. We can express this change in entropy in terms of Gibbs free energy to make it more easy to use. And hence, we can devise a criteria of spontaneity in terms of the state function of the system. That is the free energy. That is what we will be doing now. We will be trying to establish a relationship between the Gibbs free energy and the entropy. And for before doing that, some assumptions we have to consider. That is what we are discussing now. Some assumptions we have to consider. Let us look into that. So first assumption. The system is in thermal equilibrium with its surrounding at the temperature T. So the system has to be in the thermal equilibrium. System is in thermal equilibrium. Here, one very important thing we should focus. We are talking about thermal. There is a chemical equilibrium and there is a thermal equilibrium. Both are different. So here the system has to be in the thermal equilibrium. Thermal equilibrium means whatever is the change in the temperature in one direction, the same change in the temperature should be in the other direction. It means there should not be any net change in the temperature. Temperature change will be taking place because flow of energy from system to surrounding. It's not a closed system. Whatever analysis we will be doing, that we will be not doing in an isolated system. So flow of energy will be taking place, but net change in temperature is zero. That is the thermal equilibrium. So the system should be in thermal equilibrium with its surrounding. And the so when the thermal equilibrium is maintained, let the temperature be T at temperature T. So this temperature T is like a constant, we can say that, like not exactly constant, but yeah, it will be maintained. This temperature T will be maintained at temperature T. So this T is important. So this will be maintained. Second assumption. And why it is an assumption? Because in the real world, like achieving thermal equilibrium is not easy, like proper thermal equilibrium. So we are assuming that, okay, we have a system which is in thermal equilibrium. Second assumption. Heat transfer happens at the constant volume. Heat transfer between the system and the surrounding. Heat transfer between the system and the surrounding. System and the surrounding. happens at constant volume. Or I just like at constant volume. Constant volume is something which we can achieve in the real world, because whatever thermodynamic process, if I do it in a
So basically,
yeah,
in isochoric constant volume.
yeah, constant volume is isochoric process. Yeah, that's the right. Now the third assumption. Ah, instead of writing all this, we should have written isochoric process.
Yes, sir.
Nice observation. So third assumption, heat transfer between the system and the surrounding happens at constant pressure. So now we can use that isobaric.
Isobaric.
Yeah,
Isobaric.
isobaric. Yeah, isobaric. So, isochoric process, isobaric process. So these are the. Now we will do some mathematics, like some derivations. So we have a system and a surrounding and a process, a thermodynamic process is taking place, and these are some assumptions for that process.
Yes.
Now we have already seen one inequality, very famous, Clausius inequality, that I will write once again. This is related to the change in entropy. This Clausius inequality, it becomes ds, that is a change in entropy, ds, change in entropy, minus du by t, should be greater than or equal to. Now, one very interesting thing we should note, because when we studied the equation of entropy, there it was heat upon temperature. Now, how we are bringing in the potential energy here? So that we will discuss. That we will discuss. How we are getting the potential energy here. That we will discuss. So let us write some comments on this. This equation, what we got, this Clausius inequality. So this inequality holds under assumption 1 and 2. This inequality holds under assumption 1 and 2. There is a reason for that. See, basically, if that system is in thermal equilibrium, so we can say that temperature is nearly constant. Like temperature is changing, but Net change is like constant. It is maintained at capital T. And hence, in this Clausius inequality, capital T, we can use it as it is because of the system is in thermal equilibrium. And since the volume is constant, now very important observation I'm making. You know that from the first law of thermodynamics, first law of thermodynamics talks about what you say that energy, total internal energy. It says that total internal energy of the system can be changed either by doing a work or by some heat transfer. Now tell me one thing, when the volume is constant, it means that no work is done. Because displacement, no displacement will be there. No? So work done will be zero. And hence, this Q or this dQ, it will become du. Where here U is the total internal energy of the system. So we know that entropy is like dQ by T. So instead of dQ, I can write du. Why I am writing? Because of the assumption 2, that isophoric process. So in the isophoric process, this inequality holds. That is making sense. That is making sense to us. Under assumptions 1 and 2, this inequality we can use. Now with, yeah. Now with this inequality, what benefit we can get? Let us see. How further we can simplify this or use it. So I can do some shifting. I can write something like this: TDS will be greater than or equal to du. Where du is the total internal energy change in the internal energy of the system. So change in internal energy of the system will be always less than or equal to T times change in entropy. And one more very interesting observation we can make from this relation, right? This, I can say that du minus TDS, this term, du minus TDS term, this is basically, it is equal to dA. And what is this A is? A is the Helmholtz free energy. I will write for reference. Capital A is Helmholtz free energy. So now we are proceeding, like we are taking this equation towards the free energy. Helmholtz free energy. And whatever we are discussing, these all are experimental findings. And hence they are true, they hold. So once again, du minus TDS, this term, and this is what the term we are interested in, the Clausius inequality, and this term, it is equal to dA. That is a change in the Helmholtz free energy. So I can say that change in Helmholtz free energy is equal to change in internal energy minus T times change in entropy. So this relation I got. And if I move the, if I write it only in terms of A, then I can say that A is equal to U minus Ts. Only in terms of A, I can get some. Like Helmholtz free energy is U minus Ts. So this was one set of analysis. Now we will do the another set of analysis. So this I will call it the A. Now we will discuss the B. Once again, we will get back to the Clausius inequality. This Clausius inequality, it can take one more form. That is what we are discussing. And this form is Ts minus Th. H is the enthalpy by T greater than or equal. And when will the Clausius inequality will take this form? Under the assumption 1 and 3. Under the assumption 1 and 3. Like for isobaric process, this inequality will hold, and for isochoric process, the A inequality will hold. Under assumption 1 and 3. Because what is the assumption 3? Isobaric process, constant pressure. Now, one very interesting thing we have to focus. When the pressure is constant, it means that the for work done, the force involved in the work done, it will be constant. So we can say that a constant amount of work is done. Like no increase in force will be taking place. A constant amount of force is being acted and a constant amount of work is being done. Something of that sort. Now once again I can like rearrange it and I will get TDS is greater than or equal to DH. That is a change in enthalpy. And interestingly, this term DH minus TDS, change in enthalpy minus temperature into change in entropy. It is dG, where G is the Gibbs free energy. And Gibbs free energy is very popular as compared to Helmholtz free energy. Gibbs free energy. And hence we can get a relation that G is equal to H minus Ts. So now we got the relation between the free energy and the spontaneity. Because A is also a free energy, capital A, and capital G is also a free energy. Now they have different names because these free energies were invented by different scientists. Gibbs was also a scientist and Helmholtz was also a scientist. Now, based on all this discussion, one very important conclusion we can derive. A process is spontaneous, or I can say that for spontaneity, like for a spontaneous process, for spontaneity, because we have seen that spontaneous processes are the one they which occur naturally. They occur naturally. So for spontaneity, the criteria in terms of the free energy is this that we are discussing now. Delta G should be negative. I can write it D. There's a difference between delta and the small d. So small d is very, very minute. So change in Gibbs free energy should be negative, and also change in Helmholtz free energy should also be. So ultimately, change in free energy should be negative. Change in free energy should be negative means free energy should decrease. Then only it will be negative. No? If the final free energy is less than the initial free energy, then we are saying it is decreasing. So free energy should decrease, and it makes sense also, because if any spontaneous process is taking place, some energy is utilized in that process, and hence free energy has to decrease, because some of the free energy will be utilized in that process, and hence it has to be negative. If the free energy is increasing, then no process is taking place, no spontaneous process is taking place. Because in every process, some free energy will be utilized, and free energy has to decrease for a spontaneous process. This is what they are telling, and it makes sense also. Okay, now we can discuss, we can highlight, or yeah, let us move forward. Now we will discuss few different types of reactions to understand the free energy. So now let us focus on endothermic reactions. Endothermic reactions, we are already aware that
Yes, sir. The reactions which do not, which absorbs the energy.
yeah, which absorbs the heat energy.
Yes.
Yeah, that is right. So that is the endothermic reaction. And definitely for an endothermic reaction in terms of thermodynamics, we can say that change in enthalpy has to be followed. Because enthalpy is related with the heat content inside the body. So in an endothermic reaction, heat content will increase and enthalpy has to increase. So this is very. Now let us discuss it in some detail. So let me draw one graph. Like for an endothermic reaction, how the Gibbs energy, that is the free energy, changes with time for an endothermic reaction. Let us. So we are Okay, let me first draw the graphics. Let it go. Let me draw one more line. That signifies the properly. Yeah, here. Okay. Now we can mark it like what we were doing. So whenever the reaction take place, it takes place from reactants to the products. Initially, we have reactants, and after some times, that reactants they get converted into the products. This is the time axis. This is the Gibbs free energy axis. I will write it capital. Capital G is understood. It's the Gibbs free energy. Now see, the idea is that with the time, the Gibbs free energy, the graph, if we can see that, it is increasing and it will decrease. So for an endothermic reaction, for some time, the Gibbs free energy will increase. And this is very interesting observation. Because the y-axis is the Gibbs free energy value. So we can see that the value is increasing from this point to this point. So delta G is positive. And just now we have seen that for spontaneous process, delta G has to be negative. So now we will discuss. And we have already seen the formula for the Gibbs free energy that I can write it here for reference. You can make use of that formula. So change in Gibbs free energy. It is equal to enthalpy change minus TdS, change in entropy. Now, definitely in an endothermic reaction, since heat content is getting added, enthalpy will change. And if the enthalpy will change, Gibbs free energy will change. That is very sure. It is possible for the change in the Gibbs free energy, like it is possible for delta G to be negative, provided that the entropy of the system increases so much that the TdS outweighs DH. Very nice. So see, initially looking at the equation, so we say that since in the endothermic reaction, this DH term is increasing, so delta G is increasing in a positive sense. And this is what we saw experimentally also. This graph also says that. But there is a way around. The way around is that if somehow, see, T is constant, I cannot play with the T, but I can play with the ds. If somehow if I can increase this delta S, change in entropy, so that this delta S outweighs the dH, then this delta G will become negative and I will attain the spontaneity. And once I attain the spontaneity, no external work I have to done to carry that process. That process will be carried out naturally. So the idea is that from this one very important conclusion we will make, whatever observation we did, one very important conclusion we will. Endothermic reactions and it has a very good industrial application. The thing which we are discussing now. Endothermic reactions are driven by endothermic reactions are driven means automatically they become spontaneous. Naturally they will drive, are driven by the increase in entropy of the system, are driven by the increase in entropy of the system, by the increase of entropy of system. So let us suppose there is an industry wherein they are using some sort of an endothermic process to make some product, some chemical or any like pharmaceutical. Now, using this small principle, they can increase their productivity to the magical levels and they can improve the efficiency of the process. The idea is that if we increase the entropy of that process, then no need to do any external work. The input we are giving, we can minimize that because the process will become spontaneous. And once the process is spontaneous, the endothermic reaction, it is catalyzed automatically. It is catalyzed and it will automatically be driven. So this is the idea. So this very important observation we made, that endothermic reaction I can make spontaneous provided I have to somehow increase the entropy of the system. And if I am able to do that, then I can make that endothermic reaction spontaneous. And this thermodynamics is helping me in doing that. Now the second is the exothermic reaction. Like now we are analyzing the exothermic. Exothermic reactions, we know that loss of heat energy. So in such reactions, heat energy is lost. And if heat energy is lost, the heat content is lost. And enthalpy, change in enthalpy has to be negative. And a very interesting observation from the formula of the dg is equal to dh minus t ds. So naturally, exothermic reactions are spontaneous because see, this dH is negative and hence delta G will be negative. And if delta G is negative, it states that the process is spontaneous. So exothermic reactions are driven naturally. Once anything starts exploding, it will keep on exploding until all the reactant is completely destroyed. Like if you throw sodium inside water, it will keep on reacting spontaneously until all the sodium is consumed. So this is like whatever we are seeing, thermodynamics is explaining those processes. Precisely, it is explaining. Now let us look.
Yes, sir. Yes.
Yeah. And this is how firecrackers work. Because if once an exothermic reaction is initiated, it will keep on blasting, or it will keep on burning
Yes.
until all the material is consumed.
Mm.
So this is
Yes.
how it is explaining the things, the nature. So it's very interesting. Now let us look at the graph for this exothermic reaction. So we have time, we have this G, Gibbs free energy. Once again, so first let us make the curve, how the Gibbs free energy will change. So first it will increase and then it will fall, and it will decrease. So naturally, delta G is negative, and naturally the process is spontaneous. Okay, let it. So now we can just name it. So these are the reactants. Because in exothermic process, reactants have very high energy, and since energy is released, so the leftovers or the products we will be having, they will be having less energy. And interestingly, the delta G will be negative by default because energy is falling. Its energy is falling. That's negative. This is clear. This notation is. And in order to make this exothermic reaction more powerful, somehow we have to avoid TDS becoming like DS becoming negative. Like we have to avoid the decrease in entropy. If we are having a process wherein exothermic reaction is taking place and we are able to avoid the decrease in entropy, Like let if we are able to keep the randomness of the system alive, then we can improve the efficiency of the process. And if entropy is decreasing, then this ds will become more and more negative, and this will become more and more positive, and hence gibbs free energy, the decrease in gibbs free energy will decrease, like it will not be much significant. Like mathematical analysis we are doing, let's understand. So here the conclusion we can write it is that by default it is spontaneous. Like by default, so we can't like in speaking we can say that, yeah, commonly can be the right. Commonly is spontaneous. Commonly it is spontaneous. So this is also clear. Now we will discuss one more very interesting scenario that is very interesting. Let us see here also. Equilibrium. What happens at the equilibrium? At chemical equilibrium. So at chemical equilibrium, once the equilibrium is attained, there is no change in the free energy, and that is under like we can understand that. Let me use D, dg delta g both are like there is a very minute difference, but so at chemical equilibrium, once the equilibrium is attained, no change in free energy will be because no net product will be created, and hence no free energy of the system will be utilized. Whatever the free energy is utilized, the same amount of free energy is given back in the reverse direction. So no net free energy is utilized, and hence change in free energy will be zero. And at equilibrium, I can change the free energy by disturbing the equilibrium. And how I can do that? By altering the pressure or temperature. Because when the temperature and pressure I alter, the chemical equilibrium might get disturbed. And hence, as a result, Gibbs free energy will change. And that change in Gibbs free energy is what I am writing. It will be nRT. Whenever I'm talking about nRT, I'm talking about ideal gas. Log P2 by P. Or I can write it in terms of volume also. Let me write something. And this equation is for the expansion of the gas process which we have been discussing since the beginning. Okay. So now, like we saw the Gibbs free energy. Now, one more topic we will discuss. That is the spontaneity of a chemical reaction. Like whatever we have discussed until now, like we are winding it.
Yes, sir.
Spontaneity of a chemical. Now let us discuss this spontaneity of a. Okay. So spontaneity of a chemical reaction. So one very important point about spontaneity. If I talk about spontaneous reaction always favors the formation of the product. Spontaneous reactions. They favor the formation of the product. Or they take the reaction to the forward direction. They favor the formation of product. Formation of products. At reaction conditions. At conditions of reactions. Like the condition should not change. Condition is like temperature, pressure, volume. It should not change. Favor the formation of products. Condition of reaction. Conditions of reaction. Because if the conditions changes, then the spontaneity will disturb. It can disturb. Now the spontaneous reaction, one more very important, very important property of spontaneous reaction. They occur without outside intervention. They naturally occur. They naturally occur. Like some reactions, they naturally occur. They naturally occur. and they may be fast, they may be slow. It depends. Spontaneous reactions may be very fast, slow, very slow. They may be fast or slow. There is no hard and fast rule. It depends on the process. And here, two examples we can consider when we are talking about the speed of reaction. Conversion of graphite to diamond is a very slow process. And it's a spontaneous process. So interesting it is. It's a natural process, and hence we see diamond be like it is been made from the coal, hard coal. Conversion of graphite. It's a natural process, it's a spontaneous process. Conversion of graphite into diamond. And diamond is so precious. Now, though, we have devised artificial processes to convert graphite to diamond, or we have made artificial diamonds also. Conversion of graphite to diamond. It's a very slow process. It's a spontaneous process which is slow. Burning fire. See, burning fire is clear. The idea is that whenever I write about burning fire, I'm talking about the process of combustion of oxygen. That is like a very rapid process, fast, and it's also spontaneous. If I have oxygen in the atmosphere and if I initiate combustion or like LPG, and if you just initiate the reaction, you see naturally it flows, occurs. So it's a spontaneous process which is very fast. In any spontaneous process, there is always an increase in the entropy of the universe. This we have already discussed. Like one more time we can discuss it. That in the spontaneous process, entropy of the universe always increases. In any spontaneous process. In any spontaneous process. There is always an increase in the entropy. There is always an increase in the entropy of universe. And mathematically, you can write it like this. Changing entropy of the universe is equal to, so whenever there is a change in system or change in entropy of the system and surrounding, whenever any spontaneous process is occurring, it might be that entropy change in a system or the surrounding might decrease, but overall, in terms of universe, always there is an increase in entropy. Always there is an increase in the randomness. Now we will, in the context of spontaneity of a chemical reaction, we will discuss Gibbs free energy, like the final words you can say. And after all this discussion, we will conclude with the third law of thermodynamics. Then it is completed.
Okay.
Yeah. Gibbs free energy. So we are already aware of the Gibbs free energy, like some very bullet points we will discuss. Also. So whatever we have seen, we can say that Gibbs free energy is the free energy available to do work. So Gibbs free energy is basically the free energy which is available to do the work. Free energy available to do work. The free energy change of a reaction, like mathematically, let us write the equation that we have already seen. Change in Gibbs free energy. This not, it signifies standard temperature and pressure. So change in Gibbs free energy at STP, standard temperature and pressure, is equal to change in enthalpy at standard temperature and pressure minus T delta S at standard temperature and pressure. And from this, one more very interesting conclusion we can derive that we have already seen, but let's emphasize that if I talk about driving, or let me make it a different form, inside Gibbs free energy also separately. Driving forces behind all chemical reactions. Driving forces behind all chemical reactions. So there are several driving forces behind all the possible chemical reactions which we come across. And those driving forces are enthalpy change in enthalpy. I will write delta H. Change in enthalpy. Change in entropy, delta S. And change in free energy, delta G. So delta G, delta S, and delta H are the driving forces behind all the chemical reactions. And we have seen some very interesting examples also, like how these factors determine the spontaneity of a chemical reaction. And one more point I can write about spontaneous reactions. Spontaneous reactions always release free energy, and hence, for a spontaneous reaction, Gibbs free energy has to be negative. Like I will mention it somewhere here. Or let me document it. For spontaneous reactions, delta G has to be negative. It means that free release in free energy should take place. Like free energy should be consumed. Releasing free energy means free energy is consumed in a process. Release in like decrease in releasing free energy means decrease in free energy. Releasing free energy. Decrease in free energy of the system. And that decrease is because of the process, spontaneity. This is the main criteria for the spontaneity of a chemical reaction. Now we
Yes.
can make one very quick table. Then we will just discuss the third law. Then we are done. Like one very quickly, I will write it. Small observation which we have already seen. But just for completeness, we have this formula that we know delta G naught delta T delta S. Okay. Now for different conditions, delta S and delta G. Now see, the idea is very simple that delta H naught can be negative if it is, I will just write, if it is negative, and if entropy is positive, like change in entropy. If change in enthalpy is negative, change in entropy is positive, then delta G has to be negative, always negative, always negative. That we can very easily check from the equation. Always negative. If delta, like change in enthalpy is positive, endothermic reaction. And delta S is also positive. Then delta G is negative at high temperature. It means that endothermic reaction at extremely high temperature, it becomes spontaneous. And delta G is positive at low temperature. Positive at both are negative. If both delta H and delta S both are negative, then what happens? Delta G is negative at low temperature. So interesting. Like exothermic reaction involving decrease in entropy.
Yes.
Yeah, decrease in entropy. Then at low temperature, it will become spontaneous. So interesting. Yeah. And at high temperature, and hence we have seen some of the chemical reactions, they occur only at low temperatures. Positive at high. And we have positive and negative. Okay, so here it will always be positive. So no scope left for spontaneity. Always like a deadlock condition. The reaction will never be stopped in this last thing. Okay, done. Now tell me, third law, do you want to study now or in the next session?
So we can do it in the next session.
Next session. Okay. Just now. Yeah. Yeah, I can understand that tomorrow, Monday, college.